So we're going to talk about something very related but slightly different, which is the intermediate value theorem. So what is this theorem? Well, we talked about continuity before, and we definitely saw how continuity can help us compute limits, but let's go back to talking again what continuity gives us and what it says about functions. So for example, let's say that I have a function y is equal to f at x that's continuous. Well, what does a continuous function look like? Well, notably, what it looks like is and this is sort of a vague statement, but it basically says that it's something that you can draw without your pen leaving the board. So, for example, just to remind ourselves, pictures of non-continuous functions at certain points might be something like this, that has a jump here, something like, say, this, which has some awful oscillatory discontinuity at some point, or of course something that has something like an infinite jump, like 1 over x, something like this. So these guys are all things that are not continuous functions, but a continuous function is one that if you draw it, it doesn't have one of these horrible properties. Okay? So what does this mean, and what can we get from this? So let's take a look at this picture here. We see that at this point here, let's call it A. That's sort of a little a, but hey, I think I said what it is, so I think we can see it. At this point, we see that f at x is negative, and say at this point B, we see that f at x is positive. So what does that have to mean? That means that since I drew my pen from here to here, this function value, and it goes from negative on the y-axis to positive, it has to hit 0. Indeed, at this point C, for this function. So this is something that we can encode as what's called the intermediate value theorem. It's a fairly obvious statement when you have all these pictures in front of you. Why it is actually very interesting is because this is sort of, in some sense, part of the definition of what the real numbers are themselves. They have this nice property that I'm about to write down. So indeed, it's going to seem fairly obvious, but note that this being true is why we work with, say, the number line, as you might call it, in the first place. This is more of a theoretical thing in some sense, but I'll also show you how to solve some problems with it. So the intermediate value theorem says the following. So theorem, if f at x is continuous on the entirety of a closed interval, a up to b, and f at a is negative and f of b is positive, then there is some c in here such that this happens. It's a 0. So indeed, what we can do with a theorem like this is that we can find zeros of functions. So for example, we can say when the root of some polynomial exists, for example, and many other things. But this is the theorem. This is the picture thereof. We see that this is the point C that has to exist because between A and B, since our pen isn't leaving the screen, we have to cross the x-axis, which gives you a 0 of the function. Now let's do some examples to see how we can use this in practice. So now let's do 2 examples. So the first example is something that you might feel as a little bit strange, but let's do, again, this is a little more theoretical. So let's note that root 2 exists. There is a number, root 2, such that root 2 squared is equal to 2. All right, now why is this an interesting statement? Well, you may not have, but you may have seen sort of people talk about how there in fact is no rational number with this property. You can't get some fraction a over b with a and b both a whole number, which squares to 2. So this is something different. This is something that fundamentally comes from the number line itself, not just from sort of more basic number systems. So let's see how the intermediate value theorem shows us that this number actually exists. So we note that this number would have to be a root of the function f at x is equal to x squared minus 2. If you have a positive root of this function, then that's definitely going to be a number whose square is 2, because if 0 were equal to some number squared minus 2, that number squared would have to be equal to 2. So what can we do here? We can use the intermediate value theorem to show that such a number exists, because let's just note that f of 0 is equal to minus 2. And then, if we plug in f at 1, we can see that's still a negative number. That's going to be minus 1. But f of 2 is going to be 2 squared minus 2, which is 2, which is greater than 0. And of course, this is less than 0. So thus, by the intermediate value theorem, there is some c between 0 and 2 with f of c is equal to 0, i.e. that c squared is equal to 2. So this c would be our number root 2. So this is sort of an odd little thing. Perhaps you can say, oh, well, root 2 has to exist. It has to be the diagonal of a square with side length 1, so on and so forth. But this is sort of a type of mathematical argument that we can use to justify why such a number necessarily exists on the number line. And again, it's interesting because you probably have seen, or if not, you could look it up. Definitely Wikipedia has this fact, other places as well. The square root of 2 is not a rational number. So let's just do another example. So another quick example, maybe something a little less theoretical, is where do the roots of g of x is equal to, let's take a look, x to the 5th minus x minus 1 lie. So I'm not saying that we have a full algorithm to find every single root. We don't, but let's just do a little bit of an investigation, and let's note that this is a degree 5 polynomial. We don't have something nice like a quadratic formula for this. It's hard to find roots of it, but we can at least say somewhat where they're going to be. So first, let's just plug in a couple of points. Maybe let's just pick some integer points, see what we get. We see if you plug minus 1 into this, you're going to get minus 1 to the 5th minus 1 minus 1. And I guess, there's a lot of minuses here, but that's minus 1 plus 1 minus 1. So this is minus 1, which is less than 0. Okay. Well, g of 0, and again, we're just trying things out. I'm not saying we have a strong method to find where these things have to be, but let's just do a little bit of an investigation. G of 0 is also going to be minus 1. So for example, even if there is a root between minus 1 and 0, the IVT doesn't give us for sure that there is one. If we take g of 1, we see that that's, well, what's that? That's 1 to the 5th minus 1 minus 1, which, hey, is again minus 1. So we can't say for sure that there's any root on this range, but if we take g of 2, we get 2 to the 5th, which is 2, 4, 8, 16, 32, minus 2 minus 1. This is going to be 29. So this is greater than 0. So thus, by the IVT, there is some root of g of x, that is to say a 0 of the function, in the interval 1 up to 2. This doesn't tell us immediately where it is. We'd have to maybe use a computer or use the IVT more to get closer and closer to it. But nonetheless, at the very least, without any sort of graphing software, we've at least seen that this complicated function has some root, and we even know approximately where it is. And it just came from sort of some basic investigations and plugging some numbers in. So this is the type of thing that the intermediate value theorem can do for you.